Okay, let's take a look at a few examples of using the socks and shoes principle to solve equations where the unknown occurs only once. Okay, so for example, an equation like 2x plus 3 equals 11, or, let me write a couple of these up here at once, 1 plus x cubed over 16 equals 4, or maybe a third example here, 1 over x plus 2 equals 1/4. And let's go crazy. Let's put up 4 examples. How about 1 plus the 5th root of x plus 3, all of that over 5, all of that cubed, and suppose it equals 8. Okay, so in each case here we have an equation, there's one unknown, and it only occurs once in the entire equation. Okay, so how do we deal with this, and what does it have to do with socks and shoes? Well, first I want you to think about your bare foot. Here's a bare foot. There's a toe. Okay, we can do a couple different things here to your bare foot. We can wrap it in a sock. We can put a shoe on top of that. Maybe we put galoshes on top of that, and so forth. To get back to your bare foot, however, think about the sequence of events that has to transpire. You can't take off your socks first. If you have socks and shoes and galoshes on, you have to take off your galoshes first. And then you have to take off the shoes, and then you have to take off your socks. So to undo things and get back to the original bare foot, we need to take off the last thing applied first. Now, let's erase our foot here. What does that have to do with these equations? Think about x as your bare foot, and think about transforming your bare foot into a socked foot, or transforming x into the product of 2 and x, right? You've doubled it. But then we take that socked foot, or twice x, and we modify it again by putting shoes on it. In this case, we modify twice x by adding 3 to it. Okay? If I want to get back to my bare foot, back to x, I have to undo these things in the reverse order of their application, right? The last thing done has to be the first thing I undo, just like I take off my shoes before my socks. So 2x plus 3 equals 11. The last thing being done is the addition of 3. To undo that, of course, we can subtract 3 from both sides, and that's going to give us 2x equals 8. Now it's time to remove the socks, right? To undo the multiplication by 2. Of course, to undo multiplication, you divide. So if we divide both sides by 2 here, we get x equals 4. And there we go. There's our answer. Okay. Yeah, that was a very simple equation. It's a linear one, but it illustrates this very powerful principle. Let's see how things play out over here in what's essentially a cubic. Think about what happens to x and the order in which it happens according to the order of operations, right? If I were to put some sort of value in for x, if this wasn't here, let's say I was just plugging in 7 for x and evaluate this whole expression, the first thing we would have to do is add 1 to 7 to the x. Then, because that's in parentheses, right, following the order of operations, then I would need to cube it, exponentiation next, right? Then I would have to divide by 16. So the last thing that happens was this division by 16. To undo that last operation, to undo division, I need to multiply. So multiplying both sides by 16, I get 1 plus x cubed equals 4 times 16, or 64. Now the last operation that was done in the evaluation of this expression is the cubing, right? We add 1 first, then we cube. To undo cubing, we take a cube root. Taking a cube root of both sides, we have 1 plus x, right? It goes away over here, this cube. On the right-hand side, the cube root of 64 is 4. Now there's only one thing that's happening to x, right? Just the socks left. So I've added 1 to x. To undo the addition of 1, I subtract 1 from both sides, and I'm left with x equals 3. And I'm down to my answer again. What about this one? A little bit trickier here. The first thing that happens to x, what is that? Well, you could say you put it in a fraction in the denominator under 1, but that's kind of cumbersome to say. An easier way to describe what's going on here is to say we have reciprocated x, right? We just flip the fraction. It used to be x, which is the same as x over 1. Now we've got 1 over x. The next thing that happens is we added 2. The next thing that happens is we put all this in the denominator with the numerator of 1. Hey, that sounds familiar. We reciprocated 1 over x plus 2. So reciprocate, add 2, reciprocate. Now to undo that, we have to undo the last reciprocation first. How do you undo reciprocation? Let's see, if we had a fraction like 3/5 and we reciprocate it, we get 5/3. How do we get back to 3/5? Aren't we just reciprocating again? So let that be the thing we do to both sides. Reciprocate both sides. So now you have 1 over x plus 2 on the left and 4 on the right. Already it's looking much better. The last thing that happens now, looking at the left-hand side, first we reciprocate, then we add 2. That would be the addition of the 2. So undoing the addition of 2, we subtract 2 from both sides. We get 1 over x equals 4 minus 2, or 2. Now we're just down to the reciprocal of x is 2. To undo reciprocation, again, we reciprocate. So that gives us x on the left, if I reciprocate that, and 1 over 2 on the right, if I reciprocate 2. And voila, there's our answer. Even though that might have looked a little more challenging, it wasn't too bad at all. Here's one with a lot of different terms going on, but the strategy is exactly the same. Let's think about what happens to x, and in the order that these things happen. First we take a fifth root, then we add 3, then we divide by 5, then we add 1, finally we cube. Cubing was the last thing we did. So we have to undo it first. To undo cubing, take a cube root. So you have 1 plus the fifth root of x plus 3 over 5. Right? The cubing part goes away on the left if I take a cube root of both sides. Cube root of 8 is just 2. Now the last thing being done in this expression, let's see, take a fifth root, add 3, divide by 5, then add 1. It's the addition of 1. Subtract from 1 for both sides. You've got the fifth root of x plus 3 over 5 equals, let's see, I subtract 1 from both sides, I get a 1 there. Now looking at this expression, the last thing being done, you take a fifth root, then you add 3, then you divide by 5. It's the division by 5. So to undo division by 5, we multiply both sides by 5, and that's going to give us the fifth root of x plus 3, the 5 goes away, on the left equals 1 times 5 on the right. Now there's only 2 operations. Take a fifth root, then add 3. The adding 3 is the last thing that happens, so I undo it by subtracting 3 on both sides. So now I have the fifth root of x is equal to 2. And then the very last step, undo the fifth root by raising both sides to the fifth power, and we have x equals 2 to the fifth, or 32. Okay? So when you have equations where there's only one occurrence of x, things can work out very, very quickly. Okay, I'd be remiss if I didn't put up one final example here. And it's a small example, so just hang with me for one more second. 2 plus x squared equals 3. Okay, so again, the first thing that happens to x is you square it, then you add 2. So the last thing we did was adding 2, so I need to undo that. So let's subtract 2 from both sides. That's going to give us x squared equals 1. Now, there's only one operation remaining here. We squared x. We have to undo squaring x. But here's the wrinkle, right? The wrinkle in the sock. You can't undo squaring uniquely, right? All these other different operations, multiplying by 2, you can undo by dividing by 2. Cubing, you can undo by taking cube roots. Reciprocating, you can undo by reciprocating again. Taking a fifth root, you can undo by raising to a fifth power. Squaring, there's a couple different values of x here that could work. Okay, x is either plus or minus 1. Okay, so just be aware of that. Some of those operations that you see happening to x are invertible, undoable. Some are not. Okay, but still, we get to an answer fairly quickly. So there's some examples of using the socks and shoes principle to solve equations where there's one variable and there's only one occurrence of that variable in the equation.